Alright, so in this video we're learning about geometric sequences. So with the arithmetic sequences we're adding on by a constant amount each time. Geometric sequences we're going to be timesing by a constant amount each time. So you can see in this example here, you're essentially just timesing by 5 to get to the next term each time. So that's the idea behind these things. So let's do our first example, which is checking whether something is a geometric sequence. Yeah, 8, 4, 2, 1 half. So we need to be timesing by a half to get through to each next term. Or in other words, halving it to get from each next term, timesing by a half. You can see this sequence is shrinking, but if the number was bigger than one that we're timesing by, it's growing. So you call this number R. And then we sort of say that T1 is 8, T2 is 4, and so on. So show this sequence is geometric, we found the common ratio of a half, then we're going to find the general term Tn. So there's a formula for Tn, and essentially it looks like T1 times R to the power of n. So this is going to look like 8 times a half to the power of n. Now I wish I could say that, except they have some weird labeling where they have 1 as the first thing. I prefer 0 as the first thing, but the textbook does 1. So you have to sort of adjust the formula to look like this instead and take 1. Let's just check that this formula actually gives us what we want. So if I try and work out T1, it's 8 times a half to the power of 1 take 1, which is 8 times a half to the power of 0, which is 8. And T2 should be 8 times a half to the power of 2 take 1, which is 8 times a half to the power of 1, which is 4, etc., etc. So hence we can find something like T12 pretty easily. So that's going to be 8 times a half to the power of 12 take 1, which is 8 times a half to the power of 11. And if you want to do that on a calculator, you can get 8 times a half to the power of 11 there. Gives you, as a fraction, 1 over 256. So that's how you do a question like that. Next thing we have is some crazy equation like this. Essentially, to do something like this, well, you'd have to times by a ratio r there, and you'd have to times by a ratio r there. So we can actually get two equations. K take 1, if I times that by r, I should get 2k. And 21 take k, 2k times by r should give me 21 take k. We'll call this equation 1 and this equation 2. So from equation 1, I can rearrange and get r equals 2k over k take 1. And then from equation 2, I can rearrange and just, rather than 2kr, I'm going to go 2k and then plug in what I just got, 2k k take 1 equals 21 take k. And we'll just keep working through what this looks like. So let's step it out. We're going to have, if I expand all this out, I'm going to get 4k squared on the top and k take 1 on the bottom. And I'm going to get 21 take k over here. Then what's going to happen is I'm going to get 4k squared equals k take 1 can times, so I get 21 take k times k take 1. Then I'm going to get 4k squared equals 21k take 21 take k squared plus k. All right, that gives me 4k squared equals 22k take k squared take 21. Now we'll move everything to the left. So I'm going to get 5k squared take 22k plus 21 equals 0. Now that's a quadratic, believe it or not, and it's surprising that these show up, but they do a lot in these geometric sequences. So I told you quadratics were useful, they show up all the time. But essentially what you can do to solve a quadratic is you can go into polysolve. So on a Casio, that's in equation mode, or on a Texas, it won't show up on this one, but it's in app and it should be option 9. But we'll go polynomial solver. You can use like sum and product to solve these, but it's a lot easier if you just use this. Because the whole point of this topic is not really can you solve quadratics, it's can you do the geometric stuff. So we're just going to put those numbers in and then we should be able to solve it. So k should be 3 or 1.4, just like that. So if k was 3, for example, you would have like 2 and then 6 and then 18. And the sequence look like this. And you can see that we'd be timesing by 3 each time. But if k was 1.4, it would look a bit different, but it would still work. So you'd get 0.4 there, because 0.4 take 1. You would then get 2.8, and you would get 21 take 1.4, which I believe is 19.6. and all these should be timesing by 7, I reckon. Let's just check. So 2.8 times 7. Yeah, it gives you 19.6. So this is k equals, what was it? 3. And then this other one was k equals 1.4. All right. Now we got this other geometric sequence. We want to find its general term. So -6 is sort of t2. Then we're going to go to t3, t4, and t5 is 162. So I'd be timesing by r to get to all those. So if I got -6 times r cubed, that should give me 162, and I can rearrange that to get r cubed. So r equals the cube root of 162 over -6. We'll see what that is. So I can do 162 over -6, and I can raise it to the power of a third to figure out what that is. So that gives me -3. So it looks like I'm timesing by -3 each time. So if t2 is -6, then I could divide by -3 there to get t1 being +2. So that's our sequence. It goes 2 -6, and then it will go +18 because we're timesing by -3 each time. Find its general term. So the Tn formula looks like T1 times r to the n take 1. So we already saw T1 was 2 times -3 to the power of n take 1. That is the general formula. Compound interest is also an example of this. So you can see that I've got $5,000 at 7% per annum. So this could be year 1, so to speak, the start. So year 2 at the start is going to be 5,000 times, well, 1.07, because you got the 100% and the 7%. So 5,350. Year 3 and year 4, so on. So what the question's asking for is what will it be at the end of this period? So it's invested for 4 years. So it wants the start of year 5 is what it wants. So that's the number we're looking for. So essentially I can go Tn is 5,000 times 1.07 to the n take 1. And then we can just go T5 is 5,000 times 1.07 to the power of 5 take 1, which is 5,000 times 1.07 to the 4. And we'll just see what that is. $6,553.98. That's how much money they have. So compound interest is an example of this, and pretty useful one at that.